Hello, online and offline students, and it seems this is our last offline meeting during this academic year because of news. I guess you know, starting tomorrow, all exams will be online. Most probably like during last semester. I don't know precisely details of your exam on 21st of June. That is, I mean about oral examination. But concerning written exam, of course, it will be like for semester written exam during last semester. Yeah, definitely. By groups. Yeah. Yes, it is, as it was announced. Yeah, 30 points for work during semester and 30 points for the written exam and 60 points for the oral examination. So everything is according rules which you can find in the site for foreign students. I guess you know, right, about this information. Okay, so today I'll give you a sample of written exam questions. Those written exam questions were taken from former written exam questions for Russian speaking students, and in fact they're a little bit more complicated than what will be given to you because of first of all time is shorter than during usual written exams in former, I mean offline periods. And so I'll present questions for different topics. So altogether you have to solve during written exam 6 questions. So first is investigate the function and sketch its graph. Second, evaluate the integral third, determine for which alpha the improper integral converges or diverges. Fourth, determine whether the series converges or diverges. Fifth, determine whether the sequence converges pointwise or uniformly on 0, 1 and 1 infinity. Last question, 6th, determine whether the series converges pointwise or uniformly on 0, 1 and 1 infinity. So these are typical questions. And now I'll present samples for those questions. In fact, I took them from former consultations before written exam, but in Russian. So in some sense, this is just a translation of lessons in Russian, but not precisely, of course, because I took only questions and solutions. I'm sure essentially are the same, of course, but I'll present in my own fashion, definitely. So, for the first question, let's consider a couple of examples. Y equals to x squared plus 3 over 1 minus x, and y equals to cubic root of 1 minus 3 over x squared minus 1. So just a couple of examples. So let it be A, and this will be B, right? So let's start with A. We'll start with the domain. The domain of y is minus infinity minus 1 together with 1 together with 1 infinity, right? And we can determine intervals of constant sign. So here, obviously, we have positive sign for x less than 1 and negative for x greater than 1. That is, so here, y is positive, y is negative. And also, we can indicate that x equals to 1 is a vertical asymptote. Why? Because limit as x tends to 1 minus will be infinity, and limit as x tends to 1 plus will be minus infinity. That is why x equals to 1 is a vertical asymptote. Okay. We can say it was the very first stage, just to look at the function y itself. We didn't look at anything else. Okay. Next point, let's consider derivative. So derivative is 2x times 1 minus x squared plus 3 times minus 1 minus x squared, or we can rewrite it so minus 2x squared plus x squared minus x squared plus 2x and plus 3 over x minus 1 squared. Here it is not important on the square which order to choose. So y is equal to 0, or y prime, sorry, equals to 0, minus x squared plus 2x plus 3 equals to 0. We need to solve this equation, and it's equivalent to say that x minus 1, right? One solution, and x2 is 3, right? Yeah. So we can rewrite also y prime as minus x plus 1 times x minus 3 over x minus 1 squared, and we can determine signs of derivative. So let me indicate points. Minus 1, then 1 should be excluded, and 3. So what are signs? We start with minus. Minus means decreasing. Change sign at 3. Plus, increasing. Don't change sign because of square here at 1. And again change sign at minus 1 in decreasing. So looking at how signs change, we determine that minus 1 is minimum point, and here y equals to, for this minimum point, substitute minus 1, what we have 2, 1 plus 3, 4 over 2, 2. Minimum is minus 1, 2, and maximum point at x equals to 3, and it will be 9 plus 3, 12 over minus 2 minus 6. Y equals to minus 6. Okay. Third stage. Look at second derivative. So second derivative, we differentiate the first derivative. It gives minus 2x plus 2 times x minus 1 squared minus x squared plus 2x plus 3 times 2 times x minus 1 divided by x minus 1 power 4. So we may cancel x minus 1, one term, x minus 1. And after that, okay, let's understand what are powers of x. X squared, coefficient plus 2, here minus 2, no x squared. X, here coefficient is minus 4, here plus 2, plus 2, plus 4. So no x. And then term without x, minus 2 from here, minus 6. Yeah. minus 2 minus 6. All right. So minus 8 over x minus 1 cubed. So let's determine direction of convexity. So we have only one point minus 1, where convexity may change sign. And so here we have negative second derivative means convexity up, and for x less than minus 1 positive, convexity is down. No inflection points, right? Because we have no point where function is continuous and change its direction of convexity. The last stage is about other asymptotes. We have one vertical, so what happens as x tends to infinity? So look at k, limit as x tends to infinity. Plus or minus doesn't matter, so here it is not important. And we understand, divide by x, right? We should divide by x our function. And it gives limit x squared plus 3 over minus x squared plus 1, plus x, sorry. So dividing by x squared, we obtain limit 1 plus 3 over x squared divided by minus 1 plus 1 over x, and it gives minus 1. So k equals to minus 1. After that, b, the limit as x tends to infinity of our function minus x. It means we have to compute the limit x squared plus 3 plus x minus x squared over 1 minus x. It gives limit x tends to infinity, so cancel x squared. And dividing by x, we have 1 plus 3 over x, 1 over x minus 1, and it gives again minus 1. So as a conclusion, y is equals to minus x minus 1 is an oblique asymptote. Also, we can determine intersections with coordinate axes. So the only intersection is when x equals to 0, then y equals to 3. That is the only point of intersection. So the last stage, sketch the graph. So what we have here, we start with asymptotes. So we have one vertical asymptote, and one oblique asymptote. So x is 0, y is minus 1, and y is 0 for x equals to minus 1. So that is the oblique asymptote. And now what we have more, we have an intersection point 0, 3. So 1, 2, 3, this intersection. That is the point of our graph. Also, we have minimum minus 1, 2, minus 1, 2, that is minimum point. And we have maximum, x equals to 3, y equals to minus 6, 3, 4, 5, 6. So that is somewhere here. That is maximum point. And so now let us try to sketch the graph. So we have asymptote. So the graph approaches that line as x tends to minus infinity. And then it decreasing to the minimum point, like that. After that, we have increasing up to the vertical asymptote, right? Then the function changes sign at x equals to 1. So it starts from negative vertical asymptote, increases up to maximum point, and then decreases approaching the oblique asymptote. And so we obtain the graph. Okay, now for B, so here d of y, once again we need to exclude only 0, right? So now we can determine signs of our function. Let me write like that. So I want to determine when our function greater or equal or less than 0, right? So let's proceed like that. So it's equivalent to write cubic root of 1 minus 2 over x, 3 over x, 3 over x squared greater, equal, or less than 1, right? If we move 1 to the right hand side. After that, we can take cube of both sides of this equality. So that's equivalent to write like that. Or we can rewrite it moving 1 to the left hand side as, okay, x squared minus 6x plus 9 minus x squared over x squared is greater, equal, or less than 0. So we cancel x squared. And after that, we can draw the sketch of signs of our function, right? So what are signs of our function? Look, we have a sign changing at x equals to 3 over 2, right? 3 over 2, and we need to exclude 0. So what are signs? If x is large, very large, then the numerator is negative, so here it is minus, then plus, and plus. Doesn't change at 0, right? So we have only one intersection point with y-axis, only one. And also x equals to 0 is a vertical asymptote. Why? Because of limit as x tends to 0 of y equals to what? So if we substitute x tends to 0, minus 3 over x tends to plus or minus infinity, right? But taken square, it is plus infinity for sure. So we have plus infinity. And that is why we have a vertical asymptote at 0. Okay, that is the first stage. Second stage, we look at the derivative. So y prime. And we observe that we have here 1 minus 3 over x power 2 over 3. So I can write by chain rule 2 over 3, 1 minus 3 over x power 2 over 3 minus 1, it's minus 1 over 3, times derivative of this expression, which gives minus 3 times minus 1 over x squared. So altogether we have 2 over x squared times 1 minus 3 over x minus 1/3. Or maybe it will be easier to compute. X power minus 2 plus 1/3 minus 5 over 3. X minus 3 minus 1 over 3. It will be easier to compute the second derivative. So what happens with the first derivative? If we look, it is never 0, right? But we have to exclude points where it is not defined, right? Where our derivative is not defined. For x equals to 0 as before, but also one extra point, x equals to 3. So if it's greater than both of them, it increases and it changes sign because of oddness, right? Powers are odd. Cubic roots don't disturb anything, right? So we change signs of derivative, and our function was continuous at x equals to 3. Hence, here we have minimum. And this minimum is equal to what? This minimum is equal to y equals to, if x equals to 3, let's substitute. It's just 0, so minus 1. That is minimum point. Okay. Third stage. Let's look at y double prime. It's better to use the last representation. So 2 times minus 5 over 3 x power minus 8 over 3 x minus 3 minus 1 over 3 minus 1 over 3 times x power minus 5 over 3 x minus 3 power minus 4 over 3. So we can take a common denominator. Okay, 1 over 3 first of all, 2 over 3, x power minus 8 over 3, also x minus 3 power minus 4 over 3, And in brackets, we have extra minus, sorry, -2 here, -2. And so 5 times x minus 3, 5x minus 15 plus x. So what we obtain for second derivative, for convexity better to say, we have to exclude 2 points 0 and 3, 0 and 3, and here 6x minus 15 gives, so x equals to 15 over 6 or 5 over 2, right? 5 over 2 is 0, the only 0 of the second derivative. So 5 over 2 is here, 5 over 2. And you see, because of even powers, second derivative doesn't change sign at 0 or 3. And we have negative sign for plus infinity. Don't change sign, sorry, at 3. Change sign at 5 over 2. And don't change sign at 0. So x equals to 5 over 2. 5 over 2, sorry. Y equals to, okay, let's substitute x equals to 5 over 2. 6 over 5. 1 over 5. Oh. So 5 power minus 2 over 3 minus 1. That is inflection point. Inflection point. Of inflection. How it is written, inflection. E or A, oh, I forget. Can you adjust the camera? The final part is not visible. Final part is not visible, they say. Последнюю часть не видно. Вот тут.
Он как раз направил на последнюю часть.
Ага. Сейчас нормально?
Да.
Okay. So now may I erase a part? May? Okay, you have a question.
Yes, about the point of graph function, one of the points number 6 if the function is periodic, how we can find.
Oh, periodic. Don't worry about periodicity. Periodicity means you should have some trigonometric function, right? Sine or cosine or tan or cotan, right? If you haven't, no. Questions with periodic functions, definitely they will be not asked.
And about if the function is also given.
Oh, yes. Really, I forget to mention here, both functions are neither even nor odd, right? Because if you substitute minus x, what happens? It's absolutely different expression, right? And obviously you cannot transform somehow to obtain y or minus y. Same is true for that one, right? But thanks for your question, I forget to mention. Yeah, it's right, you are right. Sometimes it helps. Yeah, but sometimes. I think not in your final exam. Just a minute, I didn't finish B yet. Yeah? But if we have oblique asymptote, we haven't horizontal, right? Because either horizontal or oblique. There are some very rare examples when we have both. I mean, one as x tends to plus infinity, other for as x tends to minus infinity, right? But here we have the same infinity. In fact, I said from the beginning that here both plus and minus, right? So it means we have one asymptote, oblique asymptote, for both plus and minus infinity. Okay. Now, for the graph. Oh, not yet. The last stage, fourth, is to look at horizontal or oblique asymptote. And here you see when x tends to infinity, again, doesn't matter which plus or minus, right? We see obviously what we obtain, y equals to 0, right? So limit as x tends to infinity of y equals to 0, hence y equals to 0 is a horizontal asymptote. Of course, we cannot substitute x equals to 0, right? So we have no intersection with y-axis, and intersection with x-axis we found before, right? But there is very special point, minimum point. Why it is special? Look, here we have minimum, but derivative is not defined, right? So what happens? It means that y prime minus 3 is infinity, and which kind of infinity? Here it is decreasing, so minus infinity, right? That is minus infinity, and y prime plus 3 is plus infinity. So x equals to 3 is so-called cusp. Y equals to minus 1 is a cusp. And after that, let me draw the graph. I don't want to spend too much place for the graph. So we have vertical asymptote x equals to 0, horizontal asymptote y equals to 0. It means that both asymptotes are indicated, right? They are coordinate axes. And what else we have? X equals to 3 over 2. Somewhere here, 3 over 2. That is the 0 intersection point with x-axis. And we have minimum at 3. Okay, 3 over 2, that is 3. And this minimum is equal to minus 1. Minus 1, here it is. And, okay, 5 over 2, somewhere here is inflection point. I don't want to indicate it more precisely, but let's understand what is the graph. So you see, the function is positive for negative x, right? Positive. Hence, it approaches x-axis from above because it is positive, right? And y equals to 0 is horizontal asymptote, right? After that, it increases while we approach the vertical asymptote x equals to 0, right? And we don't change sign at 0. So the function decreases from vertical asymptote. It decreases with intersection at 3/2. And you see what's about convexity. Convexity is still convex down, right? So it looks like that up to x equals to 5/2. It is convex up, and then it changes convexity sign, convex up, and finally we come to the minimum point with vertical tangent, right? And again, x equals to 3. From the right hand side also we have vertical tangent, right? If we approach, same convexity up and approach to the horizontal asymptote. So you see cusp, right? And that is the graph. That is the graph. Okay. So to get full amount of points for this question, definitely you should investigate everything. And so rational functions, in fact, are sufficient, but maybe a little bit more complicated than I considered, but simpler than that one. Okay, then second question. Have you a question about this? No? Okay, then I'll raise it. Sorry? You see, yeah, the main thing is about maximum minimum points, inflection points, and asymptotes, of course. More points may help you, may not, by the way. Sometimes it disturbs your understanding. Okay. Sample for the second question is integral 3x plus 7 over x plus 1 squared x squared plus 1 dx. So as you see, I choose rational function, and also you need only rational functions, nothing else. Don't worry. So Here, degree of numerator is less than degree of denominator, so we don't need to make extra division, right? And please be careful and be prepared to possible division. So degree of numerator may be greater or equal than degree of denominator. Okay, so we start with partial fraction decomposition. It is a over x plus 1, d over x plus 1 squared, e over x, dx plus e over x squared plus 1. So we find common multiplier, and common multiplier is precisely the same as the same denominator as we had, right? And in numerator we have a x plus 1 x squared plus 1 plus b times x squared plus 1 plus c times x plus 1 squared times x squared plus 1 plus dx plus e times x plus 1 squared times x. Okay, so we can simplify a little bit calculations by substituting only numerators. So we compare numerators, only numerators, right? So x equals to minus 1, what it gives? In the left-hand side, it gives 4. In the right-hand side, everywhere we have x plus 1 except for b, right? For b we have minus 2, coefficient minus 2b, right? And if we substitute x equals to 0, then we have 7 equals to 0 disappeared everywhere. So only c, and c has just 1. C. So 2 coefficients we have found. 3 more coefficients. We need to compare 3 powers of x. So let's start from the largest, 4th degree. 4th degree in the left-hand side, 0 coefficient. In the right-hand side, what is with x power 4? A. B is not involved. Plus c. Plus d. Okay. Usually extreme powers help, but in our case x power 0 gives no new information, because this is precisely that one. X equals to 0, it gives just coefficient in x power 0, right? So it makes no sense. So let's start with smaller degrees than extremal. X cube. So again, 0 in the left-hand side. In the right-hand side, x cube. How we may obtain x cube? Here only one way, just a plus b here x cube, x squared times 2x, so plus 2c. And here 2x squared times dx, so 2. Yeah, and all, yeah, 2d, and also e times x cubed, right? So plus e. And let me consider, for example, x power 1. So 3 equals 2. how we can obtain x? Here only one way, just a. Here, once again, only one way, plus b. X here can be obtained to x times 1, so plus 2c. And d cannot appear as a coefficient in x, but e times x, so plus e. So let me substitute b and c. b equals to minus 2, c equals to 7. So what we have, a plus d equals to 7. Here we have 14 minus 2, 12. A plus 2d plus e equals to minus 12. Once again the same, so minus 12 plus 3 minus 9. A plus e equals to minus 9. So we have a system of 3 equations with 3 unknowns, and if we subtract, we obtain from second, third, we obtain 2d equals to minus 12 plus 9 minus 3. So d equals to minus 3 over 2. After that, if we know d, so 3 over 2 plus 7. Sorry? Minus 7. Yeah. Minus 7. Thanks. Yeah. Minus 7. Yeah. Here, minus 7. So minus 7 plus 3 over 2, it's minus 14, minus 11 over 2. A is minus 11 over 2. And substitute into the last, we have 11 over 2 minus 11 minus 18, minus 7 over 2. E is equal to minus 7 over 2. So our integral is equal to integral of minus 11 over 2 dx over x plus 1 minus 2 integrals dx over x plus 1 squared plus 7 integrals dx over x, and I can write d is minus 3 over 2 minus 3 over 2 integral x dx over x squared plus 1, and lastly is minus 7 over 2 minus 7 over 2 integral dx over x squared plus 1, and it gives so minus 11 over 2 logarithm modulo x plus 1 plus 2 over x plus 1 plus 7 logarithm modulo x. Here I can substitute x squared plus 1 equals to t, and gives dt equals 2x dx. So x dx, one extra 1/2 appears, gives minus 3 over 4 logarithm x squared plus 1. Don't need to put modulus here, it's positive always. And the last is arctan. So minus 7 over 2 arctan x plus c. Okay, that is for the integral. So third question, about series. Any question about integrals? No? Okay. Then let me erase this to wait until drying. Okay. So third question. The series is like that. Oh, sorry, sine hyperbolic here, cosine 1 over square root of n squared. We need to determine if it is convergent or divergent. So the general term is here, sine hyperbolic 1 over square root of n times cosine 1 over square root of n power n squared. That is positive for all values of n because argument of cosine tends to 0, so cosine is also positive, and hence we can use Cauchy test. So for that reason, in limit form, we need to compute this limit. So what is it? That is the limit. To take nth root means to take power 1 over n. So it means we need to compute such a limit. Square root of n times sine hyperbolic 1 over square root of n times cosine 1 over square root of n power n. Okay, what we have here. Look what happens as n tends to infinity in the base of our exponent. Sine hyperbolic t is equivalent to t as t tends to 0. Hence, what happens with this product? Tends to 1, right? Cosine tends to 1 as well. So we have base tends to 1, exponent to infinity. We considered such expressions in the first semester, right? And there was a rule how to compute limits of expressions of this kind. What you need if you have such a case, it doesn't matter, n tends to infinity or x tends to something, right? Doesn't matter, arbitrary limit. That is limit as n tends to infinity e to the power v times u minus 1. That is the rule. Why? Because also you can consider e to the power, so u power v is e to the power v logarithm u, right? And logarithm t is equivalent to t minus 1 as t tends to 1. Here I should t tends to 1, right? Okay. So this rule helps a lot. How? We compute. Okay, I can erase these things. So we can continue the calculations as follows. E to the power n times square root of n sine hyperbolic 1 over square root of n times cosine 1 over square root of n minus 1. Okay. In general, you need to be a little bit careful, or maybe I'll keep this exponent for a while. So let me write down the exponent only. Sine hyperbolic 1 over square root of n times cosine 1 over square root of n minus 1. So n times square root of n, we know the expression for sine hyperbolic with Taylor's formula. Sine hyperbolic coincides with exponential function, but only for odd degrees. So if you remember exponent, just take odd degrees, and that is for sine hyperbolic. Cosine hyperbolic only even degrees. Right, so what we obtain? 1 over square root of n, first degree, right? Then third degree should be third degree. 1 over n square root of n cube of this expression. Coefficient is 3 factorial, so 6. And larger powers. What kind of powers? Little o of powers are more than fourth. Fourth power gives 1 over n squared. Right? That is for sine hyperbolic. Then for cosine we have 1 minus, here we have alternate signs. Everything else is the same. So then next even degree, second degree, so 1 over n, and also coefficient is 2, right? And other degrees will be again little o of 1 over again, now cube n square root of n here appears. Okay, all brackets I should close except for the first one. The first one I should minus 1 and then close the bracket. So what remains? What remains? Let's compute what remains. So I'll multiply square root of n to the first. It gives n times 1 plus 1 over 6n plus little o of 1 over n square root of n times 1 minus 1 over 2n plus little o of 1 over n square root of n minus 1. That is, okay, open brackets, it gives 1 plus 1 over 6n minus 1 over 2n, and gives 3 minus 1, 2, 1 over third n over 3n, sorry, right? Minus 1 over 3n, and then all other powers will be little o of 1 over n square root of n. Oh, sorry, minus 1, right? That's important now because we cancel those units. And at the last stage, we obtain minus 1/3 plus little o of 1 over square root of n. Of course, as n tends to infinity. So we know the exponent. Let me rewrite it. We have limit as n tends to infinity, e to the power minus 1/3 plus little o of 1 over square root of n, and it gives e to the power minus 1/3, what is less than 1. What's important for Cauchy test, right? This is less than 1, hence our series converges by Cauchy test, right? So practically, the question is about how to use Taylor formula, nothing else, right? You need to compute limits, nothing else. And of course, no Cauchy test. You should note. Okay, fourth question. Integral is like that. Integral from 0 to plus infinity, e to the power alpha x, x power 3 alpha over 1 plus logarithm squared x dx. So for which alpha this integral converges, for which alpha it diverges. So first of all, we need to observe that we have two possible singularities of our function. One for sure is infinity, but another is at 0, right? It means we need to split our integral into two parts. To investigate both of them separately. Our integral converges if and only if both integrals converge. So if at least one of them diverges, then the integral diverges by the definition, right? If at least one of them diverges, right? So first part, that one, integral from 0 to 1. And here I may split it into two, as a product of two terms, right? The first term, function e to the power alpha x over 1 plus logarithm squared x, is continuous and positive on 0, 1 for arbitrary alpha, right? Doesn't matter which value of alpha we choose. This function is continuous at positive. Oh, sorry, not. I'm sorry. Sorry, no. E to the power alpha x without logarithm, of course, right? Okay. And e power alpha x is continuous at positive on 0, 1. What happens with the rest? Logarithm x tends to minus infinity as x tends to 0 plus, right? Logarithm x, right? So it means that 1 plus logarithm squared x is equivalent to logarithm squared x as x tends to 0 plus. They are equivalent. And if we have equivalent functions, then so look, because of continuity and positivity of that function, we may forget about e to the power alpha x, because it is between constants, positive constants, right? So we may apply a comparison test for integrals in both directions, divergence or convergence, doesn't matter. So if they're equivalent, so it means that this integral from the point of view of convergence or divergence, right? I don't like this sign, but it's useful. So this is equivalent from the point of view of convergence or divergence. That is equivalent to this integral x power 3 alpha over logarithm squared x. Sorry, maybe to exclude 1. Let me forget about 1. Because I'm interested only at the singularity at 0, right? Because if I let to mention here 1, what happens? Logarithm 1 is 0, and we have extra singularity which was absent in the original integral, right? And we are interested only in the integral from near 0. For example, from 0 to 1/2. Okay, and that is a modal integral, right? In fact, we considered it. So the modal integral was like from 0 to 1/2 dx over x power alpha logarithm power beta of x. So it converges when alpha should be less than 1, beta arbitrary, or alpha equals to 1, beta less than 1, right? These are only two cases when our integral converges. Hence, here instead, you see 3 alpha is in numerator, and it means, but here we have 2, it means this extra possibility doesn't appear of convergence. Extra possibility of convergence doesn't appear. It means only power of x is important for us. So converges this integral if and only if 3 alpha is greater than -1 or alpha greater -1/3. So the first part is considered. Now the second part. Oh, very long. Okay. Okay, part B. Integral from 1 to infinity. E power alpha x, x power 3 alpha, over 1 plus logarithm squared x dx. Of course, here, the main ingredient is exponent, right? Because what happens if alpha is positive? What happens? E power alpha x tends to infinity, right? As x tends to infinity. And it tends to infinity extremely fast, right? So, as we know, limit of x, let's say, x tends to infinity, of course. Let's say e to the power alpha over 2x, it is still positive, right? Alpha over 2 times arbitrary power of x and arbitrary power of logarithm, doesn't matter, right? This is infinity, right? Hence, it is greater than some constant c greater than a constant c for sufficiently large x, let's say greater than a, right? Because of infinite limit. Then what happens? So, but this integral e to the power alpha over 2x dx diverges for alpha positive, right? Obviously, right? Because this is exponent. As you integrate, it tends to infinity. And by comparison test, our integral diverges. And analogously, if alpha less than 0, then what happens with exponent? It tends to 0. And again, extremely fast, right? In such a way that now limit as x tends to infinity e to the power alpha over 2x, x to the power 3 alpha, 1 plus logarithm squared x is 0. That is 0. Exponent with negative exponent, right? When we have negative exponent, tends to 0 faster than arbitrary power of x or logarithm tends to infinity. It kills arbitrary power function or logarithmic function, right? Hence, once again, e to the power alpha over 2x, x power 3 alpha over 1 plus logarithm squared x is less than constant when x greater than a. And now, integral from 1 to infinity e to the power alpha over 2x dx converges for alpha negative. Because once again, we obtain exponent, right? And if you substitute x equals to infinity here, alpha is negative, remember, tends to 0, right? So it converges. So once again, by comparison test, this is convergent integral. So There is only one case which we need to consider separately. Alpha equals to 0, right? But what happens for alpha equals to 0? For alpha equals to 0, so B alpha equals to 0. Then we have integral from 1 to infinity dx over 1 plus logarithm squared x. That is once again one more example of a model integral. We know that integral from 1 to infinity dx over x power alpha logarithm power beta x converges when? If alpha is less than 1, beta arbitrary, and alpha equals to 1, beta, greater than 1, beta greater than 1, right? So, for our case, no power of x, right? And it means diverges, or diverges. Now we can unify both to obtain the answer. So when our integral converges, the first A is convergent for alpha greater minus 1/3, right? The second is convergent for alpha negative. So our integral answer here converges, I will write here, converges if and only if alpha belongs to the interval from minus 1/3 up to 0. That is the answer for our question. Okay, it was fourth one. Now fifth. Question 5. Let me erase. Any question about fourth? No. Okay. Okay, fifth question. Fifth question. Yes. The sequence is functional sequence, of course, n times x over square root of n minus logarithm 1 plus x over square root of n. Here the question is about pointwise or uniform convergence. Let's start with pointwise convergence. Pointwise convergence. Here, what we can do? We can write fn of x equals to n times x over square root of n minus. And we can use Taylor formula with Peano form. So Peano is allowed. Let me emphasize that using of Peano form in Taylor is suitable only for pointwise convergence. You cannot use it for uniform convergence. It's impossible in principle. Okay? So, but for pointwise, it's okay. X is fixed. So, X is fixed. n tends to infinity, so this term tends to 0, right? And we can use Taylor expansion for logarithm. Let me recall. Logarithm, that is t minus t squared over 2 plus little o of t squared as t tends to 0. So here I can use t equals to x over square root of n since x is fixed. That's important. So x over square root of n minus x squared over 2n plus little o of, okay, let me write x squared over n. Like that, firstly. That is, so what we can do, we can cancel x over square root of n. After that, I can open brackets. It gives x squared over 2 plus x squared times little o of 1 as n tends to infinity. Little o of 1 tends to 0 by the definition of this symbol, right? So it means that pointwise limit we have found. X squared over 2, and that is limit function f of x. That is true for arbitrary x, in particular x from 0 to 1 or x from 1 to infinity, right? So in both cases, we have pointwise convergence. Okay, what's about uniform? So let me start with easier part. Okay, let it be A, right? B, x belongs to 1 infinity, right? So let's consider, or better to say, not x belongs, just the interval, better to say, to indicate the interval where we study uniform convergence, right? Here we have no uniform convergence. Why? Because uniform convergence, let me write like that. So Fn tends to F uniformly is equivalent to say that limit as n tends to infinity of supremum for x in 1 infinity, this interval, right? Fn of x minus f of x equals to 0. That is uniform convergence. That is equivalent by the definition of uniform convergence. Now, supremum for x in 1 infinity of Fn of x minus f of x greater or equal than a particular value, namely, which value to choose? Obviously, square root of n is very suitable value, right? X equals to square root of n. So Fn of square root of n minus f of square root of n. Let us substitute what we have then. Fn of square root of n times 1 minus logarithm of 1 plus 1. That is Fn of square root of n. Minus f of square root of n, what is it? Minus n over 2, right? N over 2. And what we obtain? That is equal to n times modulo of 1 half, minus logarithm 2. It doesn't tend to 0, right? As n tends to infinity. In fact, it tends to infinity, right? But not to 0. So it means that this supremum cannot have 0 limit. It means no uniform convergence. No uniform convergence here. Okay, now part C. For 0, 1, we'll prove uniform convergence, so we need to consider this supremum, right? So what is about supremum? For x in 0, 1, fn of x minus f of x. That is supremum for x in 0, 1. Let me substitute. So n x over square root of n minus logarithm 1 plus x over square root of n minus x squared over 2. That is the function which we need to consider, right? Okay. Let me move. Where to move? Okay. I hope it will be enough. So equals to supremum x in 0, 1. And now what I want to do. Look. I have the following formula. 1 plus t equals 2. So before I used piano form, right? Now we cannot use it. We need to use Lagrange form. Lagrange form for remainder in Taylor formula looks like what? So what we need? I need to take, so here, second derivative, it means I should to take third derivative at a point xi, t equals to xi, when t equals to xi. And then term is quite the same over 3, right? Times t cubed. That is Taylor formula with remainder in Lagrange form. In general, you should have just first terms of your usual Taylor formula, right? And then next derivative at an intermediate point xi, let's say, right? So what is third derivative? Okay, what is third derivative? Logarithm 1 plus t, third derivative. So that is second derivative of 1 over 1 plus t. It means first derivative of minus 1 over 1 plus t squared. And that is 2 over 1 plus t cubed. That is the third derivative, right? So I'll substitute this expansion into our formula. So what we obtain? Modulus n times square brackets x over square root of n minus, now logarithm. Logarithm I replace. So instead of t, x over square root of n. X over square root of n minus x squared over 2n plus now third derivative is 2 over 1 plus t. So I'll write it here. 2 over 1 plus xi. Which power? Cube, right? Okay, that is third derivative, divided by 3 times 3, and multiplied by t cube. What is it? X cube over n square root of n. Okay, you see we have precise equality, because little o, that is something unknown, completely unknown. The only thing which we know about little o, it tends to 0 in a definite manner, right? That is the only thing which we know about little o. That is why when you write little o, you have no idea how it looks like when we consider not only values of t which tend to 0, but here you see you have x, right? And you need to take into account some knowledge about this x over square root of n. What happens with it, right? How to do it with little o? No way. Okay, that is what I rewrote. I rewrote those square brackets. Okay, square brackets should be closed. Yeah. And then minus f of x, which is x squared over 2 modulus. Okay. Let me compute what we have here. Supremum over x in 0, 1, right? What we have here. Modulo n times, in brackets, you see, x over square root of n is cancelled. So we have plus x squared over 2 minus x squared over 2 also is cancelled, right? This one cancelled, right? What remains? Only that one. You see, n times this is cancelled, so 2x cubed over 1 plus xi cubed times 3 square root of n. And now I can estimate it. Let's say equal what? X is x cubed no more than 1, right? In denominator, xi is somewhere between 0 and, where is xi? Xi is between 0 and t, right? So here xi is between 0 and x over square root of n. That is where is xi. What's important for us, xi is positive, right? So this 1 plus xi cube is greater than 1. Greater than 1. So I may replace it by 1. So what remains? 2 over 3 square root of n. And you see this tends to 0 as n tends to infinity, right? Tends to 0 as n tends to infinity. Supremum tends to 0. And it means we have uniformly convergent on 0, 1. So fifth question is over. Now the last one, sixth question. Sixth question. Okay. So which series I took? Yeah. The series is the following. Sum k from 1 up to infinity, x e to the power minus k x squared. Okay, once again, we start with pointwise convergence. When we consider pointwise convergence, we fix x. X is fixed, right? X is fixed, and it means we may write our series as follows. X times constant multiply is not important for convergence, right? And x is fixed. And here we have e to the power minus x squared power k, right? And e to the power minus x squared is some number which is between 0 and, of course, infinity. It's a positive number for any x from 0 to, not up to 1, of course, right? For any x from 0 to infinity, right? From 0 to 1, it's important, of course. From 0 to 1, right? And you know what it means. We have an infinite progression, right? The sum of infinite progression. In fact, we may compute even this sum, but it is not important. We don't need to do it, right? So it means that we have converges for any x from 0 to infinity. Okay, B. What is easier here? Here it is easier to prove uniform convergence and when we can prove it. So look, very useful tool how to prove uniform convergence. If we have a series and fk of x is less or equal than ck, and the series converges, then the series uniformly converges. Where? On E, and here also on E, this inequality, right? This inequality is valid on E, somewhere on a set, right? That is Weierstrass test. Weierstrass test. So we need to find suitable constants such that this series converges. Okay. Look, let us study for x from 1 up to infinity, right? fk of x is equal to x times e to the power minus kx squared. I want to find such a constant. How? Let's compute maximum. So I want to investigate this function on this interval, right? So I compute derivative. Derivative is e to the power minus kx squared minus 2kx squared e to the power minus kx squared. That is e to the power minus kx squared 1 minus 2kx squared. And we know about derivative now. What happens with our function from 1 up to infinity? Look, in fact, what happens from 0 to infinity? That is always positive, right? Positive. So 1 over square root of 2k appears somewhere. 1 over square root of 2k. 1 over square root of 2k, right? That is a number which is smaller than 1. So here it is decreasing, here increasing. So where is maximal value? Over 1 infinity. The function is decreasing always, right? And positive. So maximal value, fk of x, that is fk of x without modulus, less or equal fk of 1. That is maximal value. And what is this maximal value? E to the power minus k, right? E to the power minus k. And then what is sum of? That is ck for our case. That is ck, right? And then what happens? The series of e to the power minus k converges. Hence, our series converges uniformly. X e to the power minus k x squared converges uniformly on 1 infinity, right? So using Weierstrass test. Okay? That is relatively simple. Now, the last part. Okay. So the last part, C. So now we need to consider interval 0, 1. And look, if you substitute 1 over square root of k, right? It seems so, right? Then what happens from the first glance? Here we have 1 over square root of k, so e to the power minus 1, right? 1 over square root of k. Okay, the series diverges, right? But it says nothing about our series. So remember, fifth question, right? Look, we just found a particular value where our function does not tend to 0. Very good. In fact, if you are happy and you can find a value of x when general term of our series does not tend to 0, then it's okay. You have no uniform convergence. There is such a necessary test, term test for uniform convergence. But here you see that is different. This term tends to 0, right? The series diverges, but it says nothing about uniform, the absence of the uniform convergence. We cannot deduce. Okay? We need to proceed in a different way, but of course it suggests that most probably the series diverges, right? Most probably. And how to prove divergence? There is Cauchy criterion. So we use opposite to Cauchy criterion. So there exists epsilon greater than 0, such that for all capital N, there exists n greater than this capital N. There exists P natural, and there exists X in 0, 1, such that the, okay, I will use this one for simplicity. X e to the power minus k x squared should be greater than epsilon. That is an opposite to Cauchy criterion assertion, right? And as I told you, very often when you want to use Cauchy criterion to prove divergence, right? Very good idea is to choose P equals to N. That is works quite often. So We consider k from n up to 2n, and then we need to choose x. Okay, as before. So you see here how it appears. We took x equals to 1 over square root of k, right? But it doesn't help. But here, look, we fix x together with fixing n, right? So we have a possibility to choose, let's say, x equals to 1 over square root of n. Square root of n, that's important, not of k. You see, we sum up terms with k, right? But x cannot be depending on k. It's impossible. You have one x for all terms in this block, right? K varies from n up to n plus p, and x should be chosen in a unique way for all k simultaneously. So x is independent of k for sure. That's important. So I use x equals to 1 over square root of n. So we have here 1 over square root of n times e to the power minus k times 1 over n, right? And I may forget about modulus because it's positive for sure, right? Now look, I need to estimate from below, bound below. How? Okay. Exponent is a increasing function. We have minus here, so minimal value when k equals to 2n, right? So I can write e to the power minus 2n over n, right? Times sum k from n up to 2n, 1 over square root of n. And that is, what is it? E to the power minus 2. And here, how many terms we have? We have n terms, right? Times square root 1 over square root of n. Okay, I can write greater, let's say, minus 2 times square root of n. Definitely this is greater than, okay, greater than or equal than e to the power minus 2, because n is natural, right? And this is our positive epsilon, right? So it means that we have no uniform convergence. No uniform convergence on 0, 1 by Cauchy criterion. Okay, that's all. You have 2 hours, and you see, also I spent even less than 2 hours, right? And in fact, yeah, and in fact, no, 5 minutes. And in fact, I solved a little bit more, right? And also, your questions will be slightly easier. I considered more complicated questions. More techniques is involved, yeah.
In the exam, there's 30 points for each question. That means each question 5 points.
No. There is a different scale. I don't want to inform you in advance. Otherwise, you will try to learn only most expensive, let's say, questions, right? And in fact, the total sum will be greater than 30. And then there will be a scale to translate your sums into grade, into points up to 30. Up to 30, yeah. More questions? No. Then, in fact, most probably I'll do it here. I mean, in institute, but most probably I don't know if students will allow to participate. I have no idea. So I don't invite you to join me. Maybe it will be possible, but I'm not sure. Really, I'm not sure. But as far as I know, it is possible to do it online, and of course, I prefer to use special tools. Yeah. No questions. Okay. Okay. More questions? No? Then good luck for written exam, and I hope to meet you at least online in next consultation on Saturday. Definitely. Oh, I think you are with your own group. I mean, your seminar teachers will organize everything. I mean, they will check your answers. So everything is for your seminar teachers. The same, of course. The same time should be for all groups. Definitely, yeah. I think it will be chosen somewhere close to afternoon, right? Because it is more convenient for online students, as far as I know, at least. Really, I don't know details. Okay, for oral examination, still I don't know how we'll organize this distribution of students to teachers. No idea, no idea, no idea. Yeah. For oral examination, we'll discuss things. We didn't discuss it yet because you see, everything was so sudden. Yeah.
One more question about the oral exam. Our seminar, let's say, maybe one of the questions is gonna be like the whole three lecture together, and you have to write it all.
You see, now oral exam will be online, right? So you remember your first exam, right? So it will be approximately the same. So it depends a little bit about examinator, right?
Yeah, but I asked him about the ticket. Do you take the ticket?
No, how you can how you can take ticket? No tickets, of course. Yeah, no tickets, definitely. So it will be again like during winter session. Definitely, yeah. Definitely not. Definitely not. Once again, it will be the same for winter exams, right? So in general, it was recommended to be able to finish the exam during 1 hour, right? Of course, I remember I never could do it, but 1 hour and a half, usually it was more or less. Okay, and of course, it will be essentially simpler than normal oral examination, definitely. Your seminar teacher is right about, yeah. Just today I had an oral exam in Russian, and there were so different questions. I mean, one question is huge, and another is very, very easy. So, unfortunately, that is disadvantage of the system of exam tickets. For sure, yeah. Some probability story, right? More questions? No? Okay, then good luck.